Good Thursday morning. So, we just talked yesterday about neutralization reactions and all the different types of acid base kind of pairings that you may see in terms of a word equation. Now, we also need to talk about oxidation reduction reactions, or redox reactions, which we will call. And redox reactions are also considered to be single displacement reactions. So you did single displacement reactions last year. We just want to go a little bit more into detail right now. But then again, we'll have a big electrochemistry unit where we're really focusing on redox reactions themselves towards the end of second semester. So we're really just kind of touching on some stuff, bringing it up into our conversation, maybe getting a little more in-depth than what you did possibly last year. But again, all of this is just kind of, I think, very limited in what we will actually know and learn by the end of the year. Okay, so yesterday we had the 4 different types of gas formations. I just want to go back through, make sure that we review this quickly. We had any sulfide. So if I have any sulfide plus an acid, do you remember what that forms? Should form a salt, and then it should form hydrogen sulfide gas. On the next one, any carbonate or bicarbonate, so I could have carbonate or bicarbonate there, plus an acid is going to form 3 different products. It's going to form carbon dioxide, water, and salt. Any sulfite will act very similarly to a carbonate in that it will produce water and salt, but it's also going to produce SO2, okay? And remember, we had one more. So all of these, the sulfide, carbonate, sulfite, all happen when they're reacted with an acid. But then I could also react ammonium salt, so any type of ammonium salt, with a strong hydroxide, so a strong base. And remember, if we do that, what are we going to get there? We're going to get salt, we're going to get water, we're going to get NH3, we're going to produce ammonia, okay? So that was just our refresher from yesterday. Remember too that we talked about the specific wording with acid-base neutralization reactions. So if it's a strong acid, strong base, remember it will fully go to the salt and then it will go to water. However, if you have polyprotic acids, it's going to get tricky. So polyprotic acid, sulfuric acid would be one. Another polyprotic acid could be phosphoric acid. So those 2 are very common acids to use on the AP chemistry test. So those would be the ones I think that we would look at. And if there were equal number of moles of acid and base that were reacting, remember then that we'll take off 1 acid at a time, or 1 proton at a time. If we react an acid with excess base, then we're really forcing that reaction to proceed through with taking off all of the ionizable hydrogens from the acid. So it's not going to be that stepwise polyprotic acid form. Instead, it's just going to happen all at once. Okay, so that was the big difference between those acid-base neutralization reactions. All right, oxidation reduction reactions. Oh, wait, you guys, you know what we have to do? Totally forgot about this. Let's do this, comparing acid strengths, yes? Okay, so yesterday I had you look at these following solutions. So we have HX, HY, and HZ. And then you had to rank the acids from the strongest to the weakest. Okay, so hopefully we can all agree that HY would be the strongest. And it's the strongest because it's completely ionized. What makes a strong acid is the fact that it can completely dissociate into ions. It's a strong electrolyte. So I would be looking then for, if I'm comparing acid strength, the most ions that were formed from whatever salt or whatever acid that we have that's being dissolved in water. So I have most ions here in HY. Which one would be the next one? HZ should be next. HZ should be next, and then HX. HX then would be my weakest, okay? So HY, HZ, HX, because I'm looking for just the amount of ions that are dissociated. Guys, why would HZ be the next before HY? I guess before we move on, because technically I have 2 negatively charged ions here, 2 positively charged ions here, and then I have 3 positively charged ions here, 3 positive or negatively charged ions there. So HZ would have to come next because I have more ions. HX is going to have to come last because it has the fewest ions. Okay, the last one that I wanted you to try to identify for me or classify was on this slide. On the first part, so we're looking right here, we are classifying the following as a strong electrolyte, a weak electrolyte, or a non-electrolyte. So calcium chloride, that would clearly be an ionic compound, and all ionic compounds are considered strong electrolytes, so we'll call that a strong electrolyte. HNO3, that's a strong acid, so since that's a strong acid, I consider it to be a strong electrolyte. Okay. Ethanol, C2H5OH, well, it's not an ionic compound, it's not a strong acid, it's not a weak acid or a weak base, so that means it's just any other molecular compound which I consider to be a non-electrolyte. Okay? Formic acid, be right here. It's an acid. It's not one of the 7 strong acids that I need to know. It's a weak acid, so that means that formic acid is going to be a weak electrolyte. Finally, KOH, that's a strong base, or I can consider that to be an ionic compound, so that has to be a strong electrolyte. Okay, so we went from strong, strong, non, weak, strong. Okay, so on this last one, let's rank the following compounds that are dissolved in water in order of increasing electrical conductivity. Okay, so I would have to determine what's going to be the strongest electrolyte, what's going to be the weakest electrolyte, and then what's going to be in the middle. So if I'm going from increasing electrical conductivity, I want the non-electrolytes first. Calcium nitrate, that has to be a strong electrolyte. It's an ionic compound. If now I'm looking at, what is that, C6H12O6, so we're looking at glucose, that would not be an ionic compound, that would be a molecular compound, and it's not a strong acid, weak base, so it has to be a non-electrolyte here. So here's maybe the first one that I would be looking at. Then I have sodium acetate. After sodium acetate, then I have this one, which would be acetic acid, right? Because I have CH3COO, so that'd be the same thing as C2H3O2. And then with the extra hydrogen, that makes it, that's showing that it's acetic acid. Okay, so here's an ionic compound, here's an ionic compound, so strong, strong, and then I have this weak acid, which would probably be a weak electrolyte then, yes? So if I want to rank these, glucose would go first, so I would go from C6H12O6 to acetic acid, because that is a weak acid, so it's a weak electrolyte. But now I have to determine, is calcium nitrate going to give me a better electrical conductivity than sodium acetate? And here's how I would decide which one is better. When these two compounds dissociate, how many ions will they dissociate into? If I break apart and dissociate sodium from acetate, I'm going to get 1 ion of sodium for every 1 mole of ions of acetate, right? So it's a 1-to-1 ratio here. So when this breaks down, I'm going to get 2 ions. That's different if I look at calcium nitrate, because for every 2 nitrate units, I'm going to get 1 calcium ion. So I actually get 2 nitrate ions and 1 calcium ion when this breaks apart. So this gives me 3 ions, and that's going to be better at producing an electrical conductivity. So we would go glucose, acetic acid, sodium acetate, and then the best in terms of electrical conductivity will be calcium nitrate, okay? If you have questions on that, let me know, and I'll try to answer anything that you need to know. Okay, let's go to redox reactions. Let's go back. So in a redox reaction, we have actually 2 different steps that are trying to happen simultaneously. Let's say, for example, we are going to react calcium with oxygen, and in this reaction, we're going to produce calcium oxide. Okay? Oxidation is 1/2 of this step for the reaction, and oxidation occurs when an atom or ion loses electrons. So oxidation is where we're losing electrons. Reduction occurs when an ion gains electrons. So if something is losing electrons, something is going to have to pick those electrons up. So oxidation is loss, reduction is gain. There's a couple different ways that you can remember that. We can have Leo, the lion goes grr, or oil rig. Losing electrons is oxidation, gaining electrons is reduction. So Leo the lion goes grr, or oil rig, oxidation is loss, and reduction is gain. So either one that can help you remember, those are some nice little things. Okay, so oxidation, I'm losing electrons. Reduction, we are gaining electrons. One cannot occur without the other because I can't just lose electrons and then nothing else gains them. And that's because I have to have this law of conservation of charge. So if I have a reaction, then both sides of that reaction not only have to balance atomically, so you're always balancing an equation to make sure that it balances atomically, because that's just my law of conservation of matter. However, we also have this law of conservation of charge, which is very similar, and which means that the count of electrons and the count of charge on reactant and product side has to be equal. So I can't have oxidation without some type of reduction. So if you ever are having to write something out and you realize that you can't figure out what's gaining the electron, so you think that there's not a reduction, something has to be wrong, okay? Because these have to happen together. Before we do redox reactions, we have to make sure that we know how to assign an oxidation number. So you may have heard oxidation number, we can also call it oxidation state, but ultimately we're just trying to figure out what the charge of an element will have when it's in a compound, or what the charge of an element will carry if it's by itself, anything like that. So we have rules. Let's go through these rules. Elements in their elemental form have an oxidation number of 0. Elements in their elemental form have an oxidation number of 0. Guys, this one's really straightforward in that if you're looking at a reaction and you see just Fe, or maybe I give you carbon, or maybe I'll give you, I don't know, titanium. I mean to put that in brackets. These are compounds that are just, or these are elements that are just all by themselves. So I just give them an oxidation state of 0. So anytime you see something all by itself, it just has an oxidation state of 0. Okay, it's just in its neutral form. Unless it has a charge that's associated with it. So let's say that I give you Fe2+. What's the oxidation state of that one? Well, it's just going to be the charge that was given with that particular element. So if it says Fe2+, the oxidation state for iron is going to be a +2. If it's 10 4+, the oxidation state is just going to be the charge that was given to you, okay? Now, all alkali metals, oh, we forgot that too, includes diatomics. So any diatomic that you will see by itself, yes, not when, these are all just things right now that are in their elemental form, not when they're bonded with anything else, but I mean diatomics, one is bonded with the other, but anyway, when you see it all by itself, then oxidation number 0, and that includes diatomics. So Cl2, I'm going to see that with, I'm going to give that an oxidation number or state of 0. F2, 0. Oxidation number of any monatomic ion is the same as its charge. So alkali metals will always have a +1 oxidation state. Alkaline earth metals will always have a +2 oxidation number, and aluminum will always have a +3. Guys, usually where I think we see the most difficult part of figuring out an oxidation number is whenever we have these transition metals that are in the polyatomic ions, or if we have a non-metal that's in a polyatomic. But we can use all of these rules to figure out one that's missing. Okay, so non-metals tend to have negative oxidation numbers, although some are positive in certain compounds or ions. So we'll do a couple examples of this. Oxygen, usually, like 95% of the time, has an oxidation number of -2, unless it's with a peroxide ion. And peroxide will give it an oxidation number of -1. How do you know if it's a peroxide versus if it's just an oxide or an oxygen ion? Usually peroxides happen where oxygen bonds with any alkali metal. If peroxide is bonded with an alkali metal, let's just say sodium, then I'm going to see Na to O2. Okay, and I see this because I know that peroxide is O2 and sodium So if we were looking at that before, would you have canceled that to where it would say NaO? I would hope that you would, because if we see a 2-to-2 ratio, we need to simplify it into the simplest whole number ratio, which would be NaO, right? So because we have to leave that 2 there, though, for peroxide, it's showing me then that this is a peroxide. I can also look to find the oxidation number now of peroxide. So if I look at this, we just said that all alkaline metals have a +1 charge. So sodium always has a +1 oxidation state, always, okay? Well, I have 2 of them, so it's really like, even though the oxidation number or state for sodium is a +1, it's like it's carrying a +2 charge here, okay? Now, all compounds have to be electrically neutral, meaning that the oxidation state of this one has to counterbalance the oxidation state of this one. And that has to mean then that this +2 plus the oxidation state of this oxygen has to equal 0. That's my goal. Now, I have 2 of these oxygens, and then I need to figure out what the oxidation state is. So if I have a +2 here and something has to cancel out to make 0 here, that means oxygen is going to have a -1 charge in this case, which makes this a peroxide, okay? So that's why we can say that this is a peroxide. And it's really easy to pick out or distinguish peroxides, and that's because of this 2-to-2 ratio that usually happens. You would cancel it out to be a 1-to-1, so it should just read NaO, but I can't get rid of that 2 there. So, because of this, I think that it's pretty easy to distinguish peroxides. Okay, let's go to the next one. Hydrogen. Hydrogen is typically a positive one because usually hydrogen is going to be bonded to a non-metal. But there are cases that if hydrogen is acting as an anion and it's bonded to a metal, that you're going to get hydrogen to be a negative one, okay? So really that's just looking to figure out is hydrogen acting as an anion, or is hydrogen acting more like the cation? Is it bonded to a metal, non-metal, so on and so forth. Fluorine will always have an oxidation number of -1, and then any other halogen could have an oxidation number of -1, but if it's in a polyatomic ion, then usually they have positive oxidation states. So we'll look at a couple examples of that. The sum of the oxidation numbers in a neutral compound is 0. So we just said all of the oxidation states have to add up to give me an electrically neutral compound. And the sum of the oxidation numbers in a polyatomic ion must be equal to the charge of that ion. So let's maybe look to see what I'm talking about here. Okay, let's say I give you the compound potassium permanganate. So I have KMnO4, okay? So I know potassium permanganate. I'm going to place, we don't have to do this, but I'm placing brackets around this to show you, here's my alkali metal bonded with a polyatomic, and if you separate out polyatomics from what it's bonded with, I think it makes this process easier. So an alkali metal is always a +1, so I'm done with this one. I want to find the oxidation states of now magnesium and oxygen here. So permanganate has an overall charge of -1, yes? And that makes sense because here's a +1 here, this has to be a -1 here, even just to balance electrically with the compound. But now let me find oxidation state. Well, oxygen is not acting as a peroxide here, so that means that this oxidation state of oxygen is a -2. But to find the charge of manganese, I'm going to have to account for the fact that I have 4 oxygen at a -2 charge. So oxygen is really acting like it's carrying a -8 charge overall. So then the oxidation state of manganese plus this -8, that overall charge from oxygen that's carrying this -8, has to equal an overall charge of a -1. So that means that manganese has to be a +7 oxidation state. Okay, so that's how I'm going to look and decipher oxidation numbers. Let's say that I give you, let's do another one, similar to this. Let's go sodium perchlorate. Let's look at that one. Actually, let's do just chlorate. I changed my mind. Okay. So very similar. Sodium is an alkali metal. It has a +1 charge. Chlorate is a polyatomic ion. Overall, it has a -1 charge. Sodium always has a +1 oxidation state. That's always true. Now I need to pick out the oxidation state for chlorine. I need to pick out the oxidation state for oxygen. Oxygen here is not in a peroxide, so it has to be a -2 oxidation state. So ultimately, because I have 3 of these oxygens carrying a -2 oxidation number, then it's really like this is carrying a -6. So that means that chlorine's oxidation state plus this -6 overall oxidation state has to equal a -1. So chlorine in this case would be a +5 oxidation state. Okay? So hopefully doing those makes sense to you. If you want more practice picking out and deciphering what oxidation states would be, then during your bell today, somebody get out their phone and just post on the blog for me that you want more practice of this, and then I can post a couple practice problems and then the answers up to them as well, okay? And I'll do that like before the end of the school day if someone tells me that that's what they want. Okay. So let's go back and talk about redox reactions now that we know how to find oxidation numbers and all the oxidation number rules. Now, a few other, okay, in displacement reactions, so we hopefully have all, yes, I'm assuming you have all seen a displacement reaction. In a displacement reaction, we know that this is going to be typically between a metal and an acid, or a metal and some type of like metallic salt. That's usually, I think, what a displacement reaction will be. So we have a general form for a displacement reaction, and that would be A plus BX will yield AX plus B. So A plus BX yields AX plus B. So ultimately, one element is going to come and try to see if it can kick out another element in a compound, and if it's successful, then we can get a reaction. If it's not successful, then we can't get a reaction. So ultimately, these are called displacement reactions because an ion in a solution is going to be displaced or replaced, because we can call them displacement or replacement. They're going to be replaced through oxidation of an element, okay? So for example, let's say that I have magnesium and I react magnesium with hydrochloric acid. That's going to create hydrogen gas over here and then magnesium chloride. So in this problem, I would always want to try to figure out what the oxidation state or oxidation number is for each of these elements, because I know this is a displacement reaction because I have an element with a compound forming a compound and an element. That's a pretty big hint that I have displacement going on. So I assigned all the oxidation states down below, but let's check to make sure that they're correct. I have magnesium, which is at a 0, and that's just because it's a free element, which we said that those rules would give it a 0 neutral charge. HCl, hydrogen is a positive 1. Chlorine then would have to be a negative 1 here. Magnesium chloride, all alkaline earth metals have a positive 2. And since this is a positive 2, chlorine has to be a negative 1 because I have a positive 2 charge here, and then whatever the charge is of chlorine, I'd have to multiply by 2 to get it to be electrically neutral. So then that means that it would have to be a negative 1. H2, I have a diatomic here, and diatomics would just be considered in like their elemental form, so that's going to be a neutral 0 charge. So if I'm looking at this, magnesium went from a charge of 0 to a charge of positive 2. So I had some type of change in charge, yes? Hydrogen went from a positive 1 to a 0. So what's happening? Because I have a change in oxidation number, this is a redox reaction, okay? That's because oxidation and reduction have had to occur. But which one is the oxidation step and which one is the reduction step? Okay, so we just said at the beginning of the video that oxidation occurs when we lose electrons and then reduction occurs when we gain electrons. So magnesium went from a 0 to a positive 2, meaning that it is losing electrons. If something's becoming more positive, then that means it's going to be losing electrons. So magnesium, since it's losing electrons, we know that that's being oxidized. So magnesium is being oxidized. So then that means hydrogen should be reduced, because if one is oxidized, the other one has to be reduced. So if that's the case, that means hydrogen has to be gaining electrons. Hydrogen went from a positive 1 to a 0. That means it's becoming more negative, meaning that it must be gaining electrons, so it works out. Magnesium then is oxidized, hydrogen is then reduced, okay? So this is how you can also determine if something's a displacement reaction. Assign oxidation numbers to everything. If you see a change in some of the elements in terms of their oxidation state, then that means that it has to be some type of redox reaction. Okay, and then when we get into our electrochemistry unit, which is towards second semester, we'll actually do this particular lab where you'll use silver ions and oxidized copper metal. So this is just an example of a displacement reaction, okay? For displacement reactions, we usually think of these as not being reversible reactions, and that's because we have this fantastic little chart called the activity series, and we use the activity series to predict, and I think that's, yeah, it's here on the next slide. We use this activity series to predict whether a certain metal is going to be oxidized by some type of acid or by some type of metallic salt, okay? Now, different metals vary in how well they can be oxidized. So you'll see here that there's this nice big arrow, and this is table 4.5 in your book. It says ease of oxidation increases. So lithium, really great at being oxidized. It's really, really, really good in terms of oxidation. Gold just sucks. It's terrible. Hydrogen is iffy. Hydrogen is very, very iffy. Guys, and a lot of these have particular rules that are associated with them, and we'll get to that more, I think, in chapter 20. For right now, I want you to be able to maybe use this. So, activity series, like we just said, is just a list of the metals that are arranged in order of decreasing ease of oxidation. So as I go down, they become worse at being oxidized. As we go from bottom to the top, I'm going to be better at being oxidized, okay? Any metal on this list can be oxidized by the ions of the elements below it, okay? So, for example, let's look at, which one do I want to do? Let's do copper. Copper's right here, okay? Copper is above silver on my activity series, okay? Because copper is above silver, copper can be oxidized. I would say it could be oxidized by silver. So since copper is above silver, I could say copper can be oxidized by silver, okay? Same thing as lithium is above potassium. That means lithium can be oxidized by potassium. Guys, I don't have this printed for you either. I'll make copies of this for you so that way you can get an actual one of these activity series that you can look at and use. Yeah, okay. Patterns. If I give you a paper of like 20 different reactions, then you're going to have to determine, is it a metathesis reaction? And if it is a metathesis reaction, is it acid-base? Is it gas formation? Or do I have a displacement reaction or a redox reaction? So here are some patterns that maybe are some questions that you can ask to help you determine. What are the reactants? What are my reactants? So maybe if I have an element with a compound and I look at my products and see that I have another element and compound, that could be a big key that it's a single displacement reaction, okay? Are they electrolytes or are they non-electrolytes? Because sometimes that can help me determine if I have ionic compounds breaking up and maybe it's just a simple double replacement metathesis reaction where they're just going to transpose. Or are they acids and bases? Do I actually have an acid-base neutralization reaction going on? Am I going to get a precipitate? If I get a precipitate, then that's telling me that I probably have some type of metathesis reaction going on. If there's gas that's formed, that's telling me that I could have a gas formation reaction. Do the reactants engage in redox? So that's where I'm going to assign oxidation numbers, and then I'm going to determine if it's a redox reaction. So if you're stuck and you're not sure maybe kind of look and answer some of these questions, and then that could possibly help you get to the place that you need to go, okay? Guys, the last few slides is really straightforward. You have done molarity for, we did it all last year, so this should be nothing new. We already know that to calculate molarity is doing moles of solute over the volume of solution in liters. If you're mixing a solution, or if you have to dilute a solution, we've looked at that dilution calculation before. We're not going to really get into dilution and titrations because titration is the last section of this chapter. I am not going to get into titrations until we do acids. And that's because I don't think that we're going to give titrations justice by doing them in this chapter, where I want you to do several titrations, like actually in the lab, so you know what a titration is, okay? So we will talk about dilution because I think that's pretty straightforward. When we want to dilute something, we can do the M1V1 equals M2V2. So, or I could have C just meaning like the concentrated solution, and D here is just representing the dilute solution. So if I have a stock solution, I know the concentration, maybe I know the volume of that. I know how much volume I want to dilute this stock concentration or this stock solution to, but I need to figure out what the concentration will be. So we've done this before on some of the stoichiometry packets that you've had. So that's nothing new. Okay, this slide is out and this slide is out because, again, I want to wait to give titration a really good amount of justice. And the only way I can do that is for you to experience titrations first. Okay, so after this, you have a worksheet, and the first one, I have them separated out. So you're actually going to know that this is a gas formation. You're going to know this is a metathesis reaction. If you feel good with those, then tomorrow we're going to do one where they're all mixed. And you're going to have to figure out how to label them, like how would I categorize them or identify them, and how am I going to predict the products of them. So we're going to take it a little easier today on figuring out reactions, but tomorrow I'll make it even harder, okay? So we'll have more of a challenge day tomorrow. So we've got through all of chapter 4 slides, okay? Whatever questions you have, post them for me. I will answer them as best as I can today because I'll have my phone with me all day long. So if you're in class, you have a question, just post on the blog and I'll respond right back to you, okay? I'll make sure that my phone is near me during this class. If not, then your homework will be finishing up that worksheet, and then tomorrow we'll check. Tomorrow we'll also get some more practice with writing out and identifying these types of reactions that are in chapter 4, because that's really the goal of chapter 4, is to write out products, write out the reactions, and then predict what type of reaction it is. Okay, guys, you have a wonderful day, and I will see you tomorrow. Bye!